Give her about 2 minutes. Okay, great. That was last dates. I was playing.
Oh, okay.
We were talking about it last night. I think I had it on my.
I see. So on the program, you'll see I've posted the links to the YouTube videos from all the talks yesterday. Apologies to Simon. In the first 3 minutes you talked, the wireless crashed, and then we lost a few minutes, but most of it talked.
Cool.
Yeah, I'm gonna. I'll start the intro here. So welcome to Friday's session. We have a really good lineup of talks. We're going to reverse the order of the first two because it's more appropriate, and start with Christian in 1 minute. Okay. We get the late people have 2 minutes mercy.
So I set my timer to 20 minutes.
Yeah,
Just to be sure, right?
yeah.
Okay. I mean, my friends tell me that I talk too much, and the worst thing about that is they are right.
Do you set a timer when you're talking to your friends?
That's a good idea.
All right, let's get started.
Okay. Yes, welcome everybody. So I feel a little bit intimidated by being surrounded by my own slides. So if you feel intimidated as well, you're not alone. Great. So I'm going to be talking about fast and accurate emulators for nuclear scattering, in particular 2 and 3 body scattering. But before I do so, I would like to thank Dean Lee and Elizabeth for organizing this wonderful symposium here, and always being like super responsive to all the inquiries that I've had. So thank you very much for that. Okay, so as being said, as promised, I'll talk about 2-body scattering today and 3-body scattering. And so you might ask, why would we talk about emulating 2-body scattering that's already fast? Thomas alluded to this yesterday. Well, because we can make it ultra fast, and it's sort of like the prototype for, or the starting point, the launching pad for higher body scattering, such as 3-body scattering, where emulators, especially for uncertainty quantifications, are absolutely crucial. And so in the first part, I'll talk about coordinate space scattering, in particular using the matrix Numerov method. I'll talk about error estimation and emulator error estimation and propagation, and this will lead us to an active learning technique called greedy algorithm. And so then, based on this, we'll show you first results for 3-body scattering, in particular ND scattering, where we use the same technique, the same technologies, including the greedy algorithm, to do the emulation in the plane of CD and CE, so the 2, 3, and the 2, 3, and low energy couplings at N2LO below the deuteron breakup threshold. And so we swapped here the order, because essentially I give you all the technical details. I repeat the greedy algorithm that was mentioned before, and then so Abhinav has more time to discuss the exciting physics part, scattering in momentum space. And then so I would also like to emphasize, so this entire session here today is going to be very exciting. And not surprisingly, yesterday was very exciting too. And then I would like to advertise here Patrick Cook's talk later today using parametric matrix models for nuclear matter. And this is exactly what I would like you to remember. So essentially, this ab initio workflow from the bottom to the top. we start essentially from chiral EFT, chiral nuclear forces, use our many-body framework, and then make predictions for observables. Uncertainty quantifications or uncertainties apply to occur at all layers here, and we quantify them. And as we heard yesterday, emulators are key for doing this kind of uncertainty quantification in the parameters in the low energy couplings. But I would also like to emphasize that they are important for extrapolation. So for instance, in a region where we can solve the many-body Schrödinger equation, for instance, perturbatively, we can extrapolate into the non-perturbative or maybe even highly non-perturbative region, and then find high fidelity results for our nuclear observables. And so one implementation of this will be discussed in Patrick's talk in particular. Here, one of those many-body frameworks, the IMSIG medium similarity renormalization group. And if I have time, I will say a few things about recent progress on many-body perturbation theory, MBPT. So just to set the stage, so chiral effective field theory. So what we want to do essentially is to emulate scattering observables and phase shifts in the low energy coupling, specifically the contact interactions here in the two-body sector and here in the three-body sector. And then so we have our Bayesian machinery where we essentially have priors on those low energy couplings. You have seen us yesterday in a table in Thomas's talk at the posterior level, however. And then so we want to do the Bayesian parameter estimation for those coupling constants. So typically maybe of the something like 30 of those parameters. And all that we require is essentially that the potential V that has an affine parameter dependence on those parameters, and I just collect them in this parameter vector theta. And then so we have some operator structure V sub J, and then so this H here is just the affine parameter dependence. It just has to be smooth. In our case, the potential, the parameter dependence on the contact interactions here is even linear. And then so in particular, we're interested in the parameter estimation in the three-body sector. So there are only two coupling constants, but recently, so thanks to Vincenzo's and so the INT group essentially, so they found that certain diagrams are promoted or could be promoted from N5LO to N3LO and 2LO. So in fact, we have actually more than just two coupling constants here, diagrams that we can do the parameter estimation for. And in particular, it's quite interesting to see what those two quark mass dependent forces do in matter, so proportional to D2 and in F2. And of course, there has been lots of progress at N4LO, although I think they haven't really converged on the exact number of contact interactions in the three-body sector at N4LO. So anyways, there are lots of context to be emulated in, and so this is what we are gearing up for. So why scattering emulators? So I mean, scattering experiments are really like the gold standard. They yield invaluable information data for improving and testing chiral EFT implementations. So although chiral EFT is quite successful, we know that there are several issues. One, for instance, would be reproducing simultaneously the saturation density and the energy in infinite nuclear matter. And so we want to sort of like test different implementations of chiral EFT, maybe delta full, delta less, different regulator schemes, and then sort of like test whether they are statistically consistent. And to do so, we have the machinery that's Bayesian frameworks, Bayesian parameter estimation, model comparison, and so on and so forth. And so clearly here are some results missing. That's an incompatibility between Mac and Windows, so wonderful. But anyway, so I'm showing here just some applications for Bayesian parameter estimation for chiral interactions. But of course, it's much more general. So we are also interested as a community in improving optical models for scattering and reaction experiments. And so we know how to solve the scattering equations in the two and three body sector. We can do this even accurately. So that is not the problem. In fact, it's a requirement for our emulators. However, doing so repeatedly, millions of times is maybe prohibitively slow. Not in the two-body sector, as I mentioned, but in the three-body sector and higher body sector. And so we want to take advantage of emulators and the capability of removing superfluous information in the chiral interactions. So fortunately, there have been lots of emulators are on the market, so I will not go through all of them, but all of them are based on variational principles, Cohen variational principle, and a Newton variational principle. So there has been lots of progress. I also would like to emphasize the Rose emulator by the Venn collaboration. In particular, let me just emphasize the one that Thomas yesterday mentioned. So the Newton variational emulator. So this is one that works directly in momentum space and works straightforwardly in coupled channel scattering. So this is a very powerful method here. So I'm glad to see this in action and being useful. However, so none of those methods here really quantify the emulator error. So what is the error that comes from just using one of those variational principles? And this will be a theme in my talk. So we have seen this figure before. I will not go into the details here. It's just the idea of a reduced space and a reduced basis model emulator. But the point here is one should ask, so where do those snapshots that we use to train to construct our emulator, where do they come from? And so as far as I'm concerned, there are, as far as I know, there are at least two methods, commonly used methods. One is essentially scrambled over here. So cool. So this is the parameter that used to be the parameter space of just the Minnesota potential, just for as an example, one parameter here, the other one here, same here. And then so these points are just Latin hypercube sampling, so random sampling in that parameter space. And then so the POD would just do perform high fidelity calculations at all of those points. 100 in total here is just a number to give you some estimate here. So 100 high fidelity calculations, then would apply an SVD on top of it, and maybe end up with just six emulator basis points, or snapshots as we call them. So down here, as opposed to the greedy algorithm, which doesn't perform as many calculations, it starts from an initial snapshot basis, emulator basis, maybe just one, and then it estimates the error in the parameter space, and then scans the parameter space for the point where the estimated error is the largest. So this would be here in this point here, and then it adds this point to the emulator basis, and then it keeps going iteratively. It adds another point, scans the parameter space again, adds another point where the estimated error is the largest, and so on and so forth. And in this particular case, you can't really see it, but this is quite fancy here. So it does this maybe 6 times. So we have 6 high fidelity calculations. So the same number in this case. So and the key difference is the POD would have done 100 high fidelity calculations, reducing it down to 6, and the greedy algorithm only did 6 high fidelity calculations. 2-body scattering, that may not make a huge difference, but for 3-body scattering, it certainly does make a huge difference. And so the greedy algorithm is not only computationally faster than the POD in the offline stage, so training stage, if you like, but it also is capable of estimating the emulator error, both in the offline stage and in the online stage. So that's essentially.
Yeah, because I can actually share from my Mac if you want, and you just tell me.
Let's see how it goes, but thank you. Thank you very much. And so it estimates the error both in the offline stage and the online stage, and so that essentially means training stage and testing or evaluation stage of the emulator. And so this is the greedy algorithm in action. Let's just focus on one of those columns here. Let's say this one here. So this is the difference. That's the error, the absolute error in the scattered wave function for one emulator in 1D. Just to illustrate the greedy algorithm, we start with 2 snapshots, 2 initial snapshots located here. This is exactly where the emulator error is 0. Or numerically 0, because at the snapshots, the emulator reproduces the high fidelity calculations. And then it adds another snapshot where the emulator error is the largest. So in this case, it's here, right on the edge. And then it keeps going. It adds another point here. And this is exactly what you can see here. And always the error drops to 0 at the locations of the snapshots. And it does so iteratively until a certain tolerance has been achieved. It's the tolerance that you as the practitioner would specify. So we can do this not only for wave functions or scattered wave function here, but also for we can also propagate it to scattering phase shifts, and as Abhinav will show you, to scattering observables like the total cross section. So just briefly, so this emulator that Josh developed was in coordinate space, but the same idea applies in momentum space. And essentially, what it means is that one writes the scattering solver as a large-scale linear system. So here's just the parameter dependence made explicit. So there could be the Schrödinger equation, coordinate space, or the Lippmann-Stringer equation, momentum space. The latter is what Abhinav will be talking about. And as long as the potentials are affine or even linear here, so this carries through, so that this matrix and this right-hand side vector have also an affine parameter dependence. And then so you do the usual thing. So you do the reduction. So you have your snapshot matrix which builds the reduced space. Also linear combinations of the column vectors here, so the column space. And then so you just enforce using a Galerkin projection that the residual is essentially orthogonal to that subspace that expands the column space. So this is sort of like the standard Galerkin ROM. We call it GROM. We've also developed a more sophisticated, computationally more complex, which goes by the name of least square Petrov-Galerkin ROM. So here we just use the degree of freedom, the choice that we can project by essentially any matrix on the left-hand side. We choose a particular one. I will not go into the details here, but the key point is that for this LSPG, this least square Petrov-Galerkin ROM, you can show that it is free of anomalies. And anomalies called cone anomalies, and the Giri ROM in general is not. And I will show you this in a minute. And so again, here is our high fidelity model, our full order model, the inhomogeneous radial Schrödinger equation, which is just a special second order ODE, which one can solve using multiple methods. One is, and one quite popular in nuclear physics, is the Numerov method. You can write this recurrence relation as a matrix equation that makes the Numerov methods the matrix Numerov method, and then what you end up either way is a linear system that you can solve very quickly, very efficiently on the computer already at the high fidelity level. But once you do the reduction and the projection, either using Galerkin or Petrov-Galerkin projections, it's even faster. It's ultra fast. Great. So where does the emulator error estimation enter this picture here? Well, we have a linear system here. You can see it. It's over there. This linear system. And so how do we estimate the emulator error? So the emulator error is essentially the solution vector of the reduced system minus the solution vector of the full system, and then the absolute value of this. So in some norm, but computing this requires the exact solution. So what's the point? The point is that we can estimate very reliably this exact error by the residual of this matrix equation. So this is just the solution in the reduced space, and then so this is the full matrix equation, the matrix equation, the full space, and this quantity here is we use as a proxy for the true or exact error, and this object here is again still in the full space, in the full order space, the high fidelity space, but we've shown that you can actually compute this exactly in a semi-reduced space, and this is exactly where this Y, this matrix Y that enters here, the Petrov-Galerkin projection appears, resurfaces again. So in fact, there are three spaces. It's the full space. This is where the high fidelity solver lives. We have a semi-reduced space, which is close to the reduced space. This is where the error estimation lives. And then we have the reduced space where where our emulator lives and does its calculations. And so we've shown that those residuals computed in the semi-reduced space and the full space, they are equivalent. Not approximately equivalent, they are equivalent. And then so you can put rigorous bounds, theoretical bounds on this residual here if you know the smallest singular value of that high fidelity matrix here. So, but estimating singular or computing the SVD is computationally very expensive. But in applied mathematics, there are powerful methods where you, that allow you to estimate just the extremal singular values. Essentially, it's an application of the Rayleigh-Ritz variational principle that goes by the successive constraint method, or SCM. And so if you did that, you would have a rigorous upper bound on the emulator error. It cannot exceed that error. Unfortunately, even estimating this is a little bit tricky and computationally demanding because this matrix A here is non-symmetric and non-Hermitian. So there, in applied mathematics, there are very powerful and useful tools for Hermitian matrices that would make it relatively easy to estimate the extremal singular values. Unfortunately, we do not. This matrix does not meet this requirement. So we are working on this and in collaboration with an applied mathematician. And then so to show you the comparison of the POD versus the greedy algorithm. So here's a convergence pattern. Essentially the error as a function of the number of snapshots or dominant POD modes. Let me emphasize this here. So this axis here is the number of the basis size of the emulator. For the POD, that means just the dominant POD modes. So the POD has seen the entire parameter space. So we just do a Latin hypercube sampling in the parameter space, 200 random points, as you can see here, 200 points, and both emulators see those training points. However, they treat them differently. The POD performs high fidelity calculations at all 200 random points here. And then we just use the dominant modes depending on the x-axis, as defined here on the x-axis. However, the greedy algorithm only performs only however many snapshot calculations, high fidelity calculations are specified by the x-axis here. And then so as you can see, the POD is consistently the one that obtains the highest accuracy. That is really what is expected because it sees all the 200 random training points. The greedy algorithm that does not. But the greedy algorithm comes pretty close to it. So the greedy is here in blue and in orange. So what we essentially did, greedy worst and greedy best are the worst and the best initial snapshot basis that produces the largest averaged error in the parameter space for the worst greedy algorithm or worst greedy starting point, and best is the best one. And so what we then found is so POD always consistently the best, but greedy is very, very close. However, it's way less computationally expensive. And we also found, so they obtain similar accuracies, but the greedy algorithm provides error estimation. And we also found that even if you start with a relatively poorly chosen initial snapshot basis, the greedy algorithm remedies as it adds more and more points or snapshots to the emulator basis. And then so one obstacle or one difficulty that some of the variational emulators face are cone anomalies. Cone anomalies is where essentially the reduced matrix becomes singular, and then so your solution is infinite. And so this you can see this here. So the GROM is in blue and in orange is the LSP GROM. And you can see here that at this point here, the absolute error is infinite or can be infinite. This is exactly the location of a cone anomaly. However, the LSP GROM, one can show this analytically, is free of those cone anomalies. It just has a flat almost flat, in this log plot, almost flat error here. And then so the advantage of the LSPG is that it doesn't have to add a training points here or snapshot at the location of the anomaly, whereas the GROM, the greedy algorithm, finds the anomaly and then remedies it by adding a snapshot point exactly at the location of the cone anomaly. And I'm sure some of you can't see this, but maybe here it's clearer. Here's the cone anomaly in the GROM blue, and then the GROM adds the snapshot exactly at the location, thereby removing the cone anomaly. So we have also extended this in interest of time, and we also extended this with Alex and Shilin to three-body scattering below the deuteron breakout threshold. And here the cone variation in principle is actually the high fidelity model. And then we can use either a Galerkin projection or LSPG to reduce that system. And so we've applied this to proton deuteron scattering. Here you can see in this two-dimensional plane of the 2,3N low energy coupling CD and CE, how the greedy algorithm places snapshot points and reducing the overall error or uncertainty. So so this is not based on some Fadeev equations, but as I mentioned, it's based on the cone variation principle with trial wave functions obtained from a hyperspherical harmonics expansion. Okay, and so one can see this for the area and the R matrix here. The more points we add to the snapshots, so 2, 7, 12, and 17, the smaller the overall error gets. So we have like a systematic convergence. However, so this is very promising, but of course one of the challenges is to extend this to higher energies above deuteron breakup, and then emulation in all NN and 3N low energy couplings, and then the computation of scattering observables to essentially calibrate chiral interactions too. And of course, that requires not only one partial wave, so this was just one, but it would require emulation across a wide range of partial waves. So if I have 2 minutes?
No.
No? Great.
No.
Great. So then let me just say, so this is quite an exciting time for nuclear matter calculations, and we have automated many-body perturbation theory, which essentially allows us to compute up to 30,000 diagrams to 6th order. And so we have applied this to the asymmetric nuclear matter equation of state, and then used symbolic regression to find improved global parametric equations of state models. And interestingly, it finds what we know empirically is that the equation of state is essentially quadratic in the isospin symmetry. So this is quite exciting for future applications, more rigorous applications, where we find global models, because some of the Astro codes require analytical model, and of course, in general, it's quite convenient to have an analytic model. And so that Josh, I think, will be talking more about symbolic regression, nuclear physics in general later today. So I look forward to this talk. With that, to his talk. With that, let me conclude. Emulators are game changers, I think, hands down on this one. We have a greedy or active learning approach to snapshot selection in the 2 and 3 body sector, and so some promising work, but more promising results for a 3 body scattering emulation, but more work needs to be done for primary estimation of chiral NN and 3 body interactions. And then so we have a wide range of scattering emulators. I think a key question is figuring out which one is the most reliable, the most efficient by the metric of the practitioner in practical calculations of Bayesian parameter estimations of chiral interactions, for instance. Thank you so much.
Good, Patrick.
Maybe my understanding, but it seems like most of the power for the speed algorithms switching from Galerkin to Petrov Galerkin. And you mentioned this wide projector now enforcing the Petrov orthogonality instead of Galerkin orthogonality. You kind of brushed over how you got that projector. I was curious to know more details there.
Yeah, wonderful. Thank you. So let me show it here. So the greedy algorithm applies to all linear systems and all reduction methods within that realm. It's not limited to Galerkin or Petrov Galerkin. So this Y, but to answer your question, so this Y projector is, so you can essentially, so it's essentially the affine component of that matrix A times the snapshot matrix, and then you build this very wide matrix. It's a very rectangular matrix. And so the physics or the mathematics behind is that the residual lives in the column space of this matrix. And then so you can apply an SVD on this Y, and you find that it's quite low rank compared to the number of rows. This is essentially what defines the dimension of the semi-reduced space. So yeah, you can show this, and we have worked this out in our paper. That the residual, this object here, lives exactly in the parameter and in the column space of that matrix Y. Thanks.
Other questions, comments?
What makes it so much more difficult to go above the neutron breakup threshold?
So because then you break up the deuteron, right? So that's exactly the problem.
But if one has a three-body code that would allow one to do these calculations.
Oh, wonderful. Thank you so much. Great. So yes, exactly. So it's not a limitation on the emulator, it's the limitation of getting access to the closed source codes. So for us, it would be, relatively speaking, compared to those very high fidelity scattering codes and calculations, a piece of cake to develop this emulator. And I'm very grateful for you that you asked that question, because I would like to emphasize is that emulators are also a collaboration tool, right? So I understand, I've been there myself, that developing codes over years, maybe decades, one doesn't want to just put this on GitHub, but maybe developing an emulator for scattering with one of those techniques allows one to put a few megabytes in a GitHub repository and then share it without sharing the high fidelity codes, if that makes sense. And I would love to see more of this in action. And so I think the Buckeyes, so all of those codes are essentially available or will be made available soon on GitHub with documentation and annotated Jupyter notebooks.
Okay, at that point, we're right on time, so let's thank Christian again. Okay. Get the next talker. Oops. Wow. So Abhinav will take us to momentum space. So when I say 5, that means you're at the 20-minute mark. So I don't know if you're planning for 40 or 25. Yeah, I think if it's faster, go for it. Okay. Here we go. Take it away, Abhinav.
It's such here thing here. You're running out of battery.
Already?
Yeah, it goes very fast.
Let me see my slides first. Because I don't want.
Yeah, is it okay? If not, I can try to share.
They're not so clear here as I expected, but I think you can see the equations.
I
Right?
think you read mine on there.
So, yeah. So, everyone, I'll be mostly talking about the paper we recently published, which is by the collaboration of this many people. And I'm not gonna say why we need greedy algorithm. Dr. Drischler just did that in his work. And I'm just gonna say the chiral potential gives us the systematic way to get the uncertainty at each order from this slide. And for the greedy algorithm, the main calculation we are doing is this Lippmann-Swinger equation in the momentum space. And this is what it looks like for the couple channels. And if you have this, if you are solving this, and this can be rearranged to get into this nice nice matrix equation. So for our potential, this theta will be the LEC values, and these LEC values are already in the linear form. So those affine decomposition form. So, and Dr. Drischler already talked about this slide, and here's the nice picture of that, but with the audio of Dr. Drischler. So why did greedy algorithm is better than the POD approach? It's just that justification. So here's the greedy algorithm in action. So first of all, we did our toy model with the 1s0 Minnesota potential, and this is what it looks like in the coordinate space. And for our implementation, we first Fourier transform it to momentum space, and in 2D parameter space, this is what it looked like. So first, usually we do with the one snapshot. Just for this illustration purpose, I started with the 2 random sample in this parameter space, and we pick the point where the estimated error is the largest. So it picked one point. Here I'm just skipping this step. It picked one point, add to the snapshot matrix, and did the reorthogonalize that snapshot matrix and scan the parameter space, choose the point where the error is again the largest, and if the largest error in that space was below the threshold value, what it did was it stop the process, emulator was ready, and now you can do all of your calculation with the emulator. So this is what is happening. It's going from very high tolerance to the very low. So, and your residual, as you've seen in the Dr. Drischler slides, is just the norm of the T matrix equation. Sorry, the matrix equation with just the estimated T matrix here. And once we did with the toy model, we worked with the Gauger-List potential for our emulator accuracy and convergence. Like he showed in his slides, this one also follows the similar convergence pattern. It's the exponential for this couple channel, and the POD again. POD and greedy are like in the same range. Again, the POD modes you have to calculate. So here I'm using 100 sampling points. That means POD takes all 150 parameters in the parameter space in its snapshot basis and use the SPD truncation to get this dominant POD modes. While the greedy algorithm, it iteratively adds the snapshot basis. So it just has fewer high fidelity calculations. So here, this one was done from the GROM, and we got the similar results for the LSP GROM. So you can see it's exponential. And for the phase, once we had our T matrix, emulated T matrix, we propagated that emulated T matrix to phase shift. Here's one channel we selected for the deuterium channel. You can see the phase shift are the emulated phase shifts and the exact phase shifts are very close. You can see in the relative error section. We have defined the tolerance. We have emulated with the different tolerance value. Here, select. Okay. So for 10 to the power -7, the relative tolerance is here for the GROM and the LSP GROM. It goes below 10 to the power -8. for 10 to the power negative 4 is already below 10 to the power negative 5. So they are very accurate just with these, even with the 10 to the power negative 4 tolerance value. So they are very good, very accurate here. And this goes for the other channels too. We also calculated for other J values, and we got the similar results, and also for the LSP0. And then we went, how does our cross section looks like? How does our if we propagate our T matrix, emulated T matrix to cross section, you can see we got the similar results in the cross sections too. Again, these are the emulated value, the orange, and the line is the exact calculation. And again, we did with the best fit 10 to the power negative 4 tolerance value here. You can see with 10 to the power negative 4 gives you very already around 10 to the power negative 5. So and 10 to the power negative 7 it gives you even better relative error. So for the best fit is just Gaussian potential comes with the best fit LEC parameters. So that's what we are calculating for the best fit. The sample means we ran 10,000 sample other theta values, and we averaged that and we plotted that over here. You can see both sample and best fit are like close to one another. And we also did the similar thing for the LSP0, is almost same. So here, so once we did that, now our next step was to do the Bayesian parameter estimation, proof of principle for we did the proof of principle for the Bayesian parameter estimation using the cross section as an observable. So for that, we use the Buckeye discrepancy model. Here, the data we are using cross section, so I'm just going to talk about cross section here. So our experimental cross section, we assume that our experimental cross section is equal to our theoretical cross section plus the error, theoretical error, plus the experimental error, the error in the experimental, uncertainty in experimental. We assume that our experimental error is, our theoretical error is more dominant to the experimental error. So we don't have that term here. And our theoretical error is given by these two terms. One is coming from the emulated section, another is coming from our model. So EFT model we are using. So emulated error for the cross section was propagated from the T matrix. This is the norm of the T matrix, norm of the exact error from the T matrix. And again, this can be approximated by the residual, right? So residual is proportional to this one. So it can be, so you can propagate that error and use this error for our discrepancy model. And this EFT truncation error, we use N2LO for most of our calculation for two-body interaction. So EFT truncation is given by this equation. So you can see we are in the nucleon degree of freedom. So we chose our breakdown scales to be around 600 and the fine mass for the soft scale, and C bar was 1. And for this, we got our EFT, delta T EFT, something like this. where y theoretical comes from this x is the energy. At that energy, we calculated the reference value will be from the best fit LEC value. And with these two, by combining these two likelihood, we got our convoluted likelihood, which looks like this. And if this emulated error if this limit goes to 0, it becomes this normal distribution. So this is consistent with the normal distribution. If you just remove this emulated error, you just have theoretical plus EFT, and that follows this distribution. So with this in mind, and also for the prior, our mean value is the best fit LEC value, and we chose this 10% uncertainty in the best fit LEC value. Again, we can change this. We tried different values, and this is just one for the proof of principle value. So with this prior and that likelihood, we did our Bayesian calibration here. So the red one is the emulated Bayesian result from the emulated ones, and the blue one is the exact. You can see both the red ones and the blue ones line up pretty close to each other. So for this calibration, we just used our tolerance value 10 to the power -2. So we train our emulator with just 10 to the power -2. With this, even with this large tolerance value, this LEC inference was not distorted. So you can see this. You can actually use this emulated T matrix for Bayesian calibration. So then to check our emulated the efficiency of our emulator speed up, we used our Google JAX, and this work was mostly done by Jane. And you can see for different tolerance value, we first check what's the basis size for each channel. You can see for the large tolerance value, you usually end up with low basis size, and that becomes clear if you go to couple channel. Here you can see for 10 to the power -4, it's just around 20. For 10 to the power -7 is in between, is 36, 37. And here's another plot. This is the speed up, and you can see in this one, you can see how n changes if you go from here to here. This is the increment in n. How if you change n, you get higher speed up. So if you have very high tolerance value, which is around 10 to the power -4, you have less n, so you have less speed up. But if you have high n, you have very high speed up for this one. And in this one, we sort like we are using about 80 grid points for our calculation. So for our n equals to 100, the varying, which will be around this one, n equals will be in between this green one and the red one. Our speed up goes from around 26 to 72. So in between these two lines. And the speed up actually grows we also did our lock feed for this speed up, and it scales with the n to the power 2, which I haven't shown here. And this was done in the Google Jacks, and all of these potentials and these were already computed offline, and for each theta they were just the dot product for theta times this potential. So without the Jacks, I did without Jacks calculations too. So without any of these optimized solver, it actually took, even for this T matrix equation with this Gazerlis potential, initially without any optimization, it was taking me 1 day, something like that. But after using the emulator, it was just taking 1 or 2 hours. But after optimization, the speed up was like within the exact calculation was around 2 hours, and the emulator was even faster. And this is the summary of my work. And in the future, I'm gonna, on top of this emulator, I'm gonna extend this emulator to all spin dependent scattering observables. And I will use the SMS potential for the Gazerlis, for the Bayesian calibration. And then I will also like to do the comparison between the delta full and the delta less potential. Thank you.
Open for. You want to start, Keith?
Yeah, so very nice work, impressive. So for the emulator, if you were to break down, it's an impressive speed up, and the question is whether you even make it faster. And so I was wondering what the breakdown is of the various tasks in the emulator. Like where is most of the time being spent?
From my part, it was once you do while doing this Bayesian calibration. From my end, you have to calculate for different channels too. You're not just solving for one T matrix equation and calculating cross section, right? So you have to calculate J equals 1, single channel, couple channel, and from my end, it was going over those channels and actually calculating the cross section. The emulating part was really fast.
Yeah.
It didn't take too much time. The cross section part was taking much longer time for me.
Okay, interesting.
So it was for me, it was that bottleneck, but I think it can be optimized. That those calculations can be optimized and make it even more faster.
Yeah, thank you.
Other question? Do you have a time scale? Do you think that you're gonna be able to do the Bayesian things? I mean, is it just a matter of you have all the machinery?
So yeah, for this SMS potential, I think I'm
You're
gonna
waiting
be
for me, I think.
yeah. I'll be thinking for that. And yeah, I think my plan is to do this, at least validate everything like the spin dependent scattering calculation with this potential, and maybe implement this GP truncation error by this November. That's my plan.
Yep.
If
People don't know,
everything's all right.
SMS is semi-local momentum space, so it's a state-of-the-art potential from the Fulcrum group. Okay, all right, let's thank Abhinav again. And we call on Pablo. You gonna run off your computer?
You're gonna share?
No,
Were you able to download it?
Yeah, but here it's from.
I just have to use this as a backup. Thank you. So it's in the drive.
Yeah.
What do you need? So if you can download that entire folder.
The whole folder, okay. Bearing down both of them. That's big.
Yeah. Maybe you need to extract it first.
Think we're good? Okay, so what should I click on?
So click on this one. Excellent, thank you.
Good, okay.
No, I don't like it.
So it's missing stuff?
Yeah, I don't like the font. So I will share from my screen.
Okay.
I realized that Christian had that problem too with visions now.
Yeah, right.
Yeah, I think everyone has. Give me just one second. So Pablo is going to explain to us what the notation title means. Yes. And other things. Yeah. Okay. 1 second. How can I make these?
Take your time, we're ahead of schedule.
Excellent. So I'll just let you know when you're at the 20-minute point. Yes, thank you. I think we're good. All right, fire up. Thank you. Hi, folks. Very happy to be here. Has been a fantastic day and a half, well, an entire week of very good talks between this and nuclei. Today, I'm going to talk about a very complicated title, speeding up computations and model discovery. You could think that the concatenation of two speeding up operators is acceleration, but that is not exactly what I want to mean by that. So this is the outline of what I want to share with you. First, I will talk about how I see dimensionality reduction for building reduced order models in 2 steps. For me, those 2 steps are very important. Then I will talk about learning reduced equations from model or experiment data, and then my outlooks and takeaways. And basically the structure of my title, the building of reduced order modeling, I see it as you can speed up computations. I hope that I will share this tool that allows you to make that process faster. So building the emulators faster. I have this analogy of thinking that is basically going from butter to I cannot believe is not butter. And then the model discovery part is that I think inspired by how we are building the architectures of these reduced order models, we can use that to create new physical models. So instead of going directly to I cannot believe it's not butter, it's basically we're going to make a Nutella or avocado. So for me, reduced order models are part of the general idea of dimensionality reduction. Me, Kyle, and Edgar have made a very cool video of 5 minutes explaining how this entire thing works. If you want to see it, probably summarizes half of this talk in only 5 minutes. The way that I envision this is you start with a full order model, is your partial differential equation, finite element method solver, whatever is the person that wrote this, that is the actual physical model that you're using. In this case, I'm using as an example, and throughout the rest of the talk, an optical potential that calculates by expanding your wave functions into many partial waves and using a grid. It calculates by solving the differential equation, all of those wave functions, the phase shifts, and then combines all of that stuff into your cross section. This is a very big dimensional space, and that is one of the things that makes this type of solvers take a long time. The idea of building a reduced order model is thinking, can I go from my controlling parameters, which are the thing that I am interested in tuning, to my observable, or at least something approximately, by passing through a path that maybe uses less variables. That's the whole idea in here. And the benefit of that is that perhaps you end up having a better trade-off between accuracy and speed. So it's not that the emulator is going to be faster, it's that for a given accuracy,
the emulator is going to have to compute less amount of quantities, so it's going to end up being faster. I want to make the point that there's many ways that you can make these reduced order models. And here I'm just illustrating a couple of flavors of more intrusive and less intrusive ones. Usually when some people think about emulators, they may think of Gaussian processes, neural networks, or parametric matrix models. I want to distinguish the difference between you're trying to reproduce some high dimensional latent state of your original solver, or maybe you're not interested in that and you're just trying to connect inputs to outputs. For me, that is the main difference between this intrusive and less intrusive. And they have advantages and disadvantages. One of the things to think about, so if we were to extend this cat plot, computationally accuracy versus time plot, into a third dimension, you can think of how much training time and data you need to set up these things. And perhaps things that are less intrusive will need more time to be, more data to be trained, or it will take more time to train them. But there's many other benefits that you can have. For example, the development time. Perhaps setting up a neural network requires a lot of data, but it's super easy to do. You don't have to think too much. But building a reduced order model that follows all the original equations might be problematic and might take you a year and a half with you and all your friends to build up. So what I want to do is there a way that we can take our intrusive type things and build a pathway that we can end up with something that is way easier to set up, more or less at the same order of magnitude that these less intrusive reduced order models. So to do that, I'm going to highlight my vision on these things. Works in 2 steps. You have to find good reduced coordinates that describe your system or the latent states of your system. And then you have to propose and find some reduced equations that tells you how that is going to evolve dynamically. For the exact example of the scattering part that I was talking about, this compression mapping, the first part of finding reduced coordinates, you could say, I'm going to grab my wave functions in the middle and I'm going to compress them into this lower dimensional representation, which in this case can be done by a reduced basis expansion. So now your reduced coordinates are the amplitudes of these reduced bases. And to find good reduced equations, well, you could just project the original operators using the Galerkin or Petrov-Galerkin approach, and I will give you a set of reduced equations that drive that dynamic as you change the parameters. So these 2 steps, try both of them to be ideally informed by the latent objects of the full order model and the internal dynamics that you have access to. This works like a charm. There is a QR code of me and many other people talking for hours about these things. And one such approach is the reduced basis method that uses a set of informed solutions by principal component analysis or singular value decomposition on your snapshots. And then the dynamics is through the Galerkin or Petrov-Galerkin projection. This is a very cool animation that I made for varying the Wood-Saxton depth of this optical potential and seeing how the L equals 0 wave function varies as you change it. So you can see that even though this is a very high dimensional object, the trajectory that it traces in the solution manifold can be embedded, maybe with only 2 components, and these are the 2 components which are the reduced bases. This thing in the right down corner is the evolution of the coefficients as you change the parameter b, and that is what we're going to be trying to do, to build equations for. Now, this works like a charm, several order of magnitudes, speed up. We have applied to a lot of stuff, but a lot of the time it doesn't work that well. There's many problems that you can encounter. For example, trying to find these dynamics, what happens if your operators are challenging? They are non-affine, and then you have no idea how to pre-compute the projections so that your emulator remains effective. What if the linear embedding doesn't work and you want to use reduced coordinates that are not amplitude of our reduced basis, but rather something like an autoencoder? What if you have an experimental setup in where there is no equations to project? You just want to help your friends down in Sekar to make a control faster. Then that creates a problem. How are you going to make those dynamics? And even if you can create the dynamics, that doesn't mean that you should. This is an example on one of the applications that we did in 2023, using the reduced basis for a relativistic mean field. And we use a Galerkin projection on all the couple equations. This is the files of equations that I got for my reduced basis. And if you open one of them, it looks like this. And if you zoom in, it looks like that. And this is a bunch of numbers just to create the equation that controls the reduced basis coefficients as a function of the controlling parameters, which are these field coefficients that are flying around. These were like a charm. We got something that was able to evaluate this in milliseconds, mostly because Kyle is a magician, and we were able to make this simulator work. But this is a lot of redundancy on the equation side. We have to be able to do better. So, objective, can we build this easier using a handful of solutions and using the knowledge of the underlying equations? And that takes us to the main part of this talk, where we're going to discuss. So let me guide you through an example. a relatively easy one in my opinion. I have my two-body scattering, I have a Wood-Saxon potential, I'm only going to be varying the depth, and I have my solution manifold, I'm going to project into a reduced basis. So if you were to grab your original operators and you do the projection for only two bases, you end up with an equation, reduced equation that looks like that, where if you open this matrix M, has two terms, is the representation of the kinetic operator in the reduced basis and the representation of the potential operator in the reduced basis. And because this thing is affine, the potential parameter just goes out of that matrix. The whole point of what I'm trying to say is one different approach could be, instead of projecting, look at the equation that you think you will get, and then try to fit those matrix elements from data. From data in this case is model evaluations. I keep talking about this. I have been talking about this for a couple of years now. The first time that I mentioned it was in the 2023 nuclei meeting. By that time, I thought I was inventing this, and we were actually calling it in a very cute way black box galerking, because this could allow you to basically use it in any black box problem that you have. But turns out that, of course not. This has existed for many decades in the reduced order model literature, and the umbrella name that I can use to describe all of this is operator learning. And I keep saying we definitely need to do this, and we definitely need to read. And my objective today is that I hope that I can finally share some tangible results that will motivate us to actually move in that direction, because I think that is very important. So back to the example that I was talking about. The next plots are going to be heavily assisted by the agents and the new robots that we're playing with. If you want access to the codes, I'm more than happy to share them later. So I have my wave functions. Remember that we were buying the Wood-Saxon potential. I have my snapshots. I make my reduced bases. I see that the SVD, the singular values decay exponentially, so I'm good to go. The PCA doctor tells me we're in good hands. So I expand my solution in these two reduced bases, and this is the evolution of my two coefficients, my two reduced coordinates as a function of the parameter. So cool, now I need a way of finding these things. The first way that I'm going to use is by cheating. I'm going to look at the actual solution and I'm going to project. So this is a terrible emulator because you need the true solution to actually use it, but it's going to be the most accurate. The second one is going to be with the Galerkin projection, and the third one is going to be by this operator learning that I was mentioning. If you do all of these and you compare them, the main conclusion out of this is, first, this works, and second, it works better than projecting on Galerkin. It gives you solutions that in the L2 norm sense are closer to your solution manifold than the Galerkin projection. There is many reasons why that is the case, but I only have 10 more minutes to finish talking about everything else, so you can ask me that at the end, if you want. That is a very good question. Bottom line of this works, at least for this very simple case, where I'm only varying the potential depth. What about a more complicated case? What if I want to emulate the response across the 10 optical potential parameters? All of these are parameters. I need to find equations to control these things. So I want to address two important bottlenecks that you might encounter. How you're going to train this effectively. The more parameters you add, the more operators you're going to have to learn. Does that mean that you're going to need exponentially more data? Not really. And how are you going to extend these equations in a way that is effective and captures this energy? So let's think about this together. This is my example. You expand it as a 2x2 matrix. You need to learn 10 coefficients in this particular case, these four matrix elements, and these two vectors C1 and C2. If you write down this equation, this is basically an implicit equation, an implicit relationship between your controlling variable, which is your parameter V, and your response variable, which are the two reduced coordinates. This is what defines an implicit relationship between these two things. And this big lambda that I'm putting in there is basically the hyperparameters that you tune to change this implicit relationship between these two things. So you can just treat this as a machine learning problem in a classical sense. You define a cost function, like I-squared, which is going to be the difference between the actual least square cheating coefficients that I want and whatever my current method is giving me. And you optimize that. You have a training CSV table in Excel that has the columns of the controlling thing and the two responding things, and you just optimize this thing. You make a graph, the thing trains in like, I don't know, a minute or so. If you're clever and you put an initialization on all of your numbers that is inspired by the Galerkin projection on your operators, you actually converge much, much faster. But still, this takes a while, and this is a very simple system. But what if you consider doing the following instead? You grab your implicit relationship, where these are unknowns, and you just plug your values in here. You grab your controlling potential V, you plug it in here, and you grab your two response variables and you plug them in here. If you do that, this equation is no longer zero, of course, because you have not found these lambdas that makes it zero. but it's a residual. You can minimize with respect to lambda. And if you do that, now this is a linear problem in lambda, the thing that we're trying to optimize. So you can solve it in one shot. And this is something that Daniel Xu, which is an amazing undergrad that has been working with me for the last year and a half, pointed out to me last Friday. And all of the results that trickle after this are being possible thanks to the fact that now we can train these things in one shot. Daniel will be applying for grad school and internships in the next months and years. So for the people in here that are looking for very good people to work with, I encourage you to talk with them. Not only you can solve it in one shot, so now you train this not in a minute, but in half a millisecond, which is faster than Rose computes the online stage, but it's also more accurate. For whatever reason, it converges to a solution that ends up being better at representing the relative error in the dynamics of your coefficients as a function of the parameter B. By the way, the gray box is the training data. Everything outside of that is extrapolation. As you do this and you transform this into a linear problem, your linear solver can tell you, by the way, your design matrix was ill-conditioned. I found 15 or 14 directions that didn't actually matter for your problem. And then you realize you can massage this equation and put it into something that is less redundant. In this particular case, making this matrix the identity matrix removes all of those redundancies, and then you can even train this faster. So that is the first part. The second part, how are we going to extend our equation shape for more parameters? Well, we did this. You could grab your optical potential stuff and just start adding terms proportional to your parameters. That will not scale very well. That will not take into account cross counters between the different parameters elements. So what I thought of doing, let's follow what the Rose paper did. Instead of thinking about the parameters driving your dynamics, think of the potential itself driving your dynamics. And what we're going to do, we're going to evaluate the potential that we have access to at some locations that I call predictors, and those are the ones that are going to drive the dynamics. So you call these things P, you expand on those predictors P that depend on all the parameters all together. There is an effective way of finding where to evaluate these things. It's called the Maxwell algorithm. And that's it. That's how you derive your dynamics. I also forgot to mention, right now, for those of you that know the details on this, I'm not expanding this around a free solution. I'm expanding it around a central solution, a central value of the parameter that I'm interested in obtaining the manifold around. Details don't matter. I want to make the point that although this is technically a matrix and it depends on parameters, this is not a parametric matrix models in the way that the folks that are developing these things are using. I'm not using the eigen system of this matrix. This is an equation that is an implicit equation between my controlling parameters and my response variable, and the relationship ends up being inverting a matrix, multiplying it by a vector. So be careful with that, because the way that you approach the problem might lead you to what are the next steps that make sense to apply to your to what you're trying to achieve. Let's put all of this together. So I have my mapping projecting using the reduced basis of my solutions. I'm going to drive the dynamics in this way. I still am thinking of how to call this operator learning reduced order model. So for now, on everything that you see, I will just be putting LROM, or learning reduced order model. So I grabbed all the points that we had in the Rose paper. So 10-dimensional parameter space. I sample all of that 30% variation of all of the parameters, and this thing works like a charm. In here, you see the full order model in black. In grayish, the noise floor that you will get if you were to cheat with a reduced basis of 4. In red, the linear reduced order model that you will get if you just expand on your parameters. And in golden, the one that you get when you expand on predictors. And you can check on many of these cross sections, the pattern seems to be the same. We are able to reproduce these things like really well. And if you look at the distribution of errors, that sustains that. If you go to a cat plot, which is a computational accuracy versus time plot, this is the one that we had on the original Rose paper. The bottom line of this, because I'm running out of time, is that this works better than Rose. It's almost an order of magnitude faster. It's almost 2 orders of magnitude more accurate. And it was way easier to train. And I have 2 cool demonstrations that I want to share with you. So my first demonstration is, this is an HTML that basically shipped one of these emulators and allows you to play with it. So you can change all the parameters of the optical potential, and this is running in real time, the response, which is your cross-section, as a function of these controlling parameters. So that's how fast these things can work now. And the accuracy is less than 1% problem. Now, this one is almost the same, but instead of varying across the 10 parameters, what I'm varying is the Koning-LaRoche global parameterization. All of the parameters depend on energy and depend on the isotope number. So if you see on the left, here's the region where I train for all the calcium isotopes from 30 to 60. This is calculation, so I can make calcium 30 and 60, nobody will complain. And lab energies between 10 and 30 MeVs. And as I move in here, if you look on the middle, it's basically the cross section as you're changing isotopes. So I'm able to emulate across isotopes and energies. And this was not difficult to do. And if you click in here, this takes you to different full order model calculations pre-computed. And you see that in some cases it has some trouble, but it makes sense. I'm extrapolating like crazy in isotope and energy. So these are my two demos. Let me go back to my thing. Okay, so we have achieved a global optical potential reduced order model that is faster, more accurate, faster to train, and easier to set up. Easier to set up, I did this in a week, granted, thanks to the help of a lot of AI, but Daniel Odell and I took more than a year in developing all the equations and all the interconnectivity that ROSE needed. All of this was possible thanks to the work of lots of people and decades of reduced order model developments. And now it's time for my annual rant about nomenclature. At vector continuation, we had the discussion yesterday, and I expressed my very strong beliefs. This is the timeline. 2018, Dean and friends came up with this brilliant idea. And these are all steps that we were walking towards to trying to make this emulator that I just showed you work. In particular, as Christian was telling, around 2020, we were dealing with Kohn anomalies and trying to see how we can make the emulator at least faster than the full order model. And we were struggling because there were many things that we didn't know how to do. If in 2004, somebody would have pointed out to us that the empirical interpolation and all of this exist, probably by now we will have U uncertainty quantify n-body scattering global optical potential, which is something that people that work on these things really need. Who knows? Maybe we'll have also flying cars by now. But that's why I think that it's important to call these things by the name so that we thermalize with the literature and we advance in the direction that we need. So what exactly we did? We found these good coordinates. We obtained a set of training optimal coordinates to compare, and then we created the dynamics in the way that I described. Nothing of this really is constrained to scattering. So I really think that now we are in the position to apply these to basically everything that we can think of that I'm putting in there in the screen of many of the talks that I have. So my vision for making reduced order models in the future, you basically sit down with your friends under a tree, and your friend basically describes what their full order model more or less is doing. And you start coming up with ideas on how the reduced equation will look like. And you just try it. You feed them to data. This is what Lauren will be talking about later. And if you have the right shape for the equation, it just works. I'm going to take 1 extra minute. Can I have 1 extra minute, Dick?
You actually have 4.5 minutes.
Oh, fantastic. This is, for me, this is the most important thing that I want to share with you, even though the other things were also nice. So let me take a minute to breathe. I think I was aiming for 20 minutes instead of 25. Okay. What does this mean? If this really works, that means that I have an abstract model space where I'm going to represent my current model by an arrow, and I have this extremely flexible way of making my learned reduced order models. I have this orange arrow that can get relatively close then to the blue line. But if I grab then, I change my model to something that is still a reasonable model and is still in the same category, well, my orange arrow will change. Will then follow that new model. And if I have a collection of reasonable models, I will reasonably expect that by tweaking the internal dynamics of my reduced order model, I can approximate the entire thing. But if this can adapt to any reasonable model, and the only thing that it requires is data, like an inspiration of the equations that you have, and the data can be wave functions, but maybe it can be also cross sections. What happens if I put the experiment there? Can we use this in a smart way to create a better model, not to emulate the models that we have already come up with? So the way that I think about this is that now you have I'm going to make the picture blow up a bit. You have the span of all these reasonable models that you're thinking of. This requires a lot of work, a lot of creativity from a lot of physics people that are thinking, what am I going to put in my optical potential? How am I going to change my parameters, etc., etc. This is already a hugely information-rich manifold that is telling you around where reasonable models move. But if you want to improve this, the way to change these knots on the full order model part is coming up with new terms for your potential or changing the parameters of that. That might be restrictive. You might have some biases that you're not able to find. the whole point that I'm trying to think is that perhaps if you get to train these things to reproduce what reasonable models do, then by very gently tweaking the internal connections of this thing, you might be able to get closer to experiment just by adjusting that extra mile, that extra inch to try to meet the experimental pattern. So let's try it. Thank you very much, Cal Bayer, who is in the airport right now, but who provided actual neutron scattering data to me and kept answering my text yesterday very late at night. What I'm going to show you right now, this is my experimental angular distributions for neutrons across many isotopes. It's all the corpus data that was used for the Conning de la Roche paper and various MEVs. I'm going to use one of my flexible learn, reduce, order models with 6 bases and 9 operators. And I split the training and testing of 84 curves, so not points, curve, for train and 24 for test. This is extremely preliminary. I did this last night, so results might change, but I want to illustrate the point and say that seems to be working. So this is the emulator evaluated at the Conning de la Roche parameterization. I was surprised that it's already doing a good job. I didn't have to think. The thing is the emulator is already extrapolating in isotope and energy. And that is the data, some selected values. And this is a green thing that you obtain. If you slightly mess up, you have to do it very carefully. If you mess it too much, the thing starts becoming crazy. But if you mess with those connections in those matrices just a little bit, you end up getting closer in the training data almost all the time, in the testing data, some portion of the time. But this is basically the future that I want to walk towards. And I think that this will be framed as a machine learning, physics-informed machine learning approach, because the first part of training these to reasonable models is extremely important. You cannot not do that. So I'm not saying we should replace our way of doing models with this alone. No, it's going to be a correction on top of it. So my vision for making models in the future, you sit beneath a tree with your favorite theorist, and you ask them to describe the actual physical problem that they want to tackle in as much detail as possible, and in a very blurry way, the mathematical model that they think they could use for this. Very blurry, so that you see it, you get inspired, and you think, what will be the reduced order model equivalent of this blurry picture? And then you tweak that to your experimental data. So, outlooks and takeaways. This is so cool. I have had a blast playing with this for the last years, but in particular in these last months of development of doing these things in this way, makes you feel extremely powerful. You can make a lot of reduced order models and you can discover new models. Now I hope that my title structure makes sense. And it's very easy to do. You just need to find good reduced coordinates, and then you just need to find good reduced equations for those coordinates. Ideally implicit equations between the coordinates and the controlling parameter. And whoever can tell me why this is the case, I have been talking about this for years, you will receive a cookie from me. The final thing, I see a community-driven future ahead of us. As machine learning gets more and more, these AI things, the robots, gets more and more good at doing things, we might risk not talking to each other and just talking to the machine. So let's try to make extra efforts so that we can come up as a community to still be sharing all the progress that we do. And with so many problems and so many approaches, I think what we need to do is create spaces to play together. Cal and I have been talking about this for a while, and we basically worked a lot and realized that we were reinventing Kaggle. If you have never heard of Kaggle, I didn't before I reinvented it with Cal. Go online and look at it. It's a place to basically put challenges so people can tackle your challenges with different machine learning approaches. We're putting up this reduced order model for optical potentials challenge with the data set with everything that we did. I encourage everybody here that is interested to give it a try. Imagine if we could convince not only the theorists, but also our experimental friends to give us problems there, to put in there, I don't know, data from the controlling setup for SECAR. And then we can just all try different algorithms to make this science drive to progress together. And with that, I'm going to thank all the people that paid for my lunch, all my friends and collaborators, and I open the floor for questions. Thank you. Thank you.
I can start. Oh, you want to go?
So it's one of the goals now to find a better parameterization for the optical potential.
But a better optical potential as a whole. I see finding a better parameterization will be kind of like trying to find this arrow. You know, you tweak in parameter space and you arrive there, but you're still biased, which makes sense. That's the whole point of having a model that is not hyper tuned. once you did that, I think that to move in this direction, small tweaks in the reduced order model equation can get you there without destroying the generalization or predictability power of the model. That's my hope.
But just staying within the model, how optimal or unoptimal has been the KD parameterization?
I have no idea. I think it works in some ways, but I have the pictures. I mean, it doesn't do a terrible job, but it also messes up some things. Thank you. More questions?
So, we talked before, and I'm very invested in the implicit view of argument. But I'm curious how if you've dealt with okay, so everything here is scalar. And so not knowing exactly what those reduced coordinates are is fine. I'm talking about what results you have with your optimum. So you're not predicting an eigenvector. So how do you take this implicit RBM idea or operator? And when you don't know your reduced coordinates, how can you still make predictions in the full vector space instead of just scalars?
Can you give me a concrete example of a situation where that happened?
Yeah, so imagine eigenvector continuation or just, finding eigenvectors of an affine Hamiltonian, but you're not doing an explicit reduced basis. But don't want to construct your reduced operators directly, you want to learn them from data, but you still want to predict full line.
If I understand you correctly, I think the picture that I want to share is this one. It's basically thinking, even if you don't have actual access to these vectors, knowing how the underlying model works can give you an idea on what to use to create the architecture of your reduced order model. For example, with Cal, we're playing right now with DFT to do these things. One way could be you literally go, by Cal, you literally go, and he doesn't want to get in trouble. You literally go and train it in the same way that I did with the scattering by looking at the solutions. Or you say, I have access to the output calculations of these things, binding energy, charge radii, maybe densities, etc. And the reduced order model that you made is mimicking what you think you will get if you will have projected everything. Now, if you do that, and you do not have access to the eigenvectors, the final vectors that your model has are meaningless or don't have an associated representation in there, but the dynamics is correct. So for example, knowing that this thing is iteratively and self-consistent, I will concatenate a bunch of matrices together and saying the eigenvector of this matrix gets dot product with this other thing, square, that controls some of the matrix elements of this one, and then you get inspired by that to make the architecture of your thing, even if you don't have access to the latent space of the full order. Does that make sense?
Oh yeah, it makes sense.
Sure.
So let me ask, your examples, like with the optical potentials, it's got parameters that vary a small amount, 30%, something. Is anything breakdown if you have something more like the chiral case where you want to fit things subleading parameters that are going to vary, in natural units from -5 to 5 or something like that?
I don't know, right? Because I have
It
never.
would be nice to see
Yep.
how that did. And
It's for what I saw,
there's no reason I have to think things
Yep.
won't work, but
Yep.
it's just the little tweaks are kind of.
yeah, I extrapolated by a long shot in those things, but at the end,
Yeah.
it's so problem dependent that if I tell you I extrapolate 50 plus minus 30, it doesn't matter. Your thing might change way more by something. So I don't know. We'll have to try. But it's very easy to try. That's the whole point that I'm trying to make.
Okay, I got a final question. So in thinking about your last things with your models and going all that, how do you fit that in with a picture of doing model discrepancy, Bayesian model discrepancy?
For me, the applications that I have seen of Bayesian model discrepancy, which I haven't seen that much, are usually at the level of the output. Is you have the prediction, you have, for example, a mass table, and to the mass table, you add a correction. This that I'm saying, I'm still in the operator. I haven't solved the problem yet. What I'm modifying in here is the underlying mechanics of the internal structure of the predictor, not the final output. That's the difference that I will see. Does that make sense? I don't change the final predictions and change how the model gets to those predictions by moving in operator space in a way that makes sense.
Yeah. Okay, guess maybe I have to think a little bit more.
Me too. These are not fully cooked ideas. Anybody wants a cookie? Anybody had an idea why implicit?
All right, so hopefully we have timed this, so as we speak, coffee is arriving outside. I don't know if it is or not, but maybe that's where Kyle went. So let's thank Pablo again. So we resume at 10:30.